సబ్స్క్రైబ్ చేయండి. ఫర్ మోర్ అప్డేట్స్ బెల్ ఐకాన్ క్లిక్ చేయండి. ప్లీజ్ లైక్ అండ్ షేర్ చేసి కామెంట్ చేయండి.
Hall effect. When a magnetic field is applied perpendicular to a current carrying conductor, a potential difference is developed between the points on opposite side of the conductor. Let us consider this is the current carrying conductor. This is the current carrying conductor. This current carrying conductor is placed in XYZ coordinate system. XYZ coordinate system. The Hall effect is the production of voltage difference. The Hall effect is production of a voltage difference across an electrical conductor. The Hall effect is the production of a voltage difference across an electrical conductor, that is transfers an electric current in the conductor. For example, we applied the magnetic field on this electric conductor, perpendicular to the current carrying conductor. Then potential difference is produced between at this point. At this point the potential difference is produced. Okay, this is the current carrying conductor. The current is flow in this current carrying conductor in this direction, x direction. But we applied the magnetic field perpendicular to the electric field. This is the magnetic field B. This is the magnetic field B. This is the magnetic field B. So the magnetic field applied on the current carrying conductor perpendicular to the flow of the current. When the potential difference is developed between this point and this point, the opposite sides. The potential difference is developed between the points on opposite side of the conductor. This is the opposite side, this is the opposite side. So according to Hall effect, when a magnetic field is applied perpendicular to a current carrying conductor, a potential difference is developed between the points on opposite side of the conductor. This is the Hall effect. Consider a uniform thick rectangular metal strip. This is the metal strip. This metal strip placed with its length parallel to x-axis. This is the x-axis. Let a current I is passed on the conductor along x-axis, and a magnetic field B is the developed along y-axis. Okay, the force F is established perpendicular to xy plane. The force is developed along to xy plane. The direction of this force along to z axis. Due to magnetic field, the charge carriers due to this magnetic field, the charge carriers experience a force by moves with drift velocity. So the current charge carriers moves with the velocity. That moving velocity is called here drift velocity. This drift velocity is represented by V suffix d. This is the drift velocity. The force is established by magnetic field. F is equals to, we know that, Q of V cross B. V cross B. Okay. Then what is the here V? V is the velocity. F is equals to Q. What is the V? V is the velocity, drift velocity, V suffix D. B is the magnetic field. Therefore, F is equals to Q B V D. This is the equation number 1. This is the equation number 1. This equation is writing is a Q B V D. This is the first equation. Okay. Next, another force, the force established by electric field. This force is established by magnetic field. Now this force established by electric field, that electric field here VH, Hall electric field. So then the force is equals to electric field into charge. The force is equals to, what is the electric field here? Hall electric field. Hall electric field is known as the Z direction, that is the Q. F is equals to EHQ. This is the Z direction. Z direction is known as the Hall direction. So this is the equation number 2. This is the equation number 2. This force is established by the electric field. This force is established by the magnetic field. From equilibrium condition, these two forces are equal. These two forces are equal. These two forces are equal. That is equals to, force is equals to Q B V suffix D is equals to EZQ. Then Q is the cancel, remaining VZ is equals to B into V suffix D. This is our third equation. This is our third equation. Finally, the potential difference VH is developed between two faces of metal strip. This potential difference is called Hall voltage. Hall voltage. The motion of charged carriers towards the upper face or below face of metal strip will continue until the potential difference is built up. So the potential difference, then potential difference is the here VH is equals to, what is the formula of the potential difference? Electric field into distance. VH is equals to, what is the electric field? Is equals to Hall electric field D. Okay, this is our fourth equation. This is our fourth equation, where D is the length between two faces. Here D. Okay, from equations 3 and 4. This is the 3. This is the 4. This is the 3. From equations 3 and 4, VZ is equals to B into VD, that is equals to EZ is equals to VZ or VH is equals to VH upon D. Okay, then the third equation is the third equation from fourth equation. BVD is equals to VH upon D. Then Vd is equals to Vh upon Vd. This is our fifth equation. Vz or Vh is equals to once is the B into V suffix d, another is the Vh is equals to Ezd. From this equation, Ez is equals to Vh upon d. From this equation d. Yes. Okay. Finally, Vd is equals to Vh upon Bd. This is our fifth equation. Our fifth equation. If small n is the number of charge carriers per unit volume. So if n is the charge carriers per unit volume, the current density, then the current density is known as the J. Here J is equals to n number of charge carriers, the charge into drift velocity. This is the current density. The formula of current density is equals to number of charge carriers into charge into drift velocity. Here charge is also known as charge is nothing but E. This is also current density. Here drift velocity is known as J upon Ne. This is our sixth equation. What is the fifth equation? Fifth equation is equals to Vd is equals to Vh upon Vd. From these two, this is the fifth equation. This is the sixth equation. From 5 and 6, LHS are equals, then RHS are equals. Then these two equations can be written as Vh upon Bd is equals to J upon Ne. But Vh upon D is equals to Ez or Eh, Hall electric field, and also this is the transverse electric field, same as. Okay, therefore J upon Ne is equals to, this is the Vh upon D. Vh upon D is equals to Ez or Vh. So totally this value can be written as E suffix H upon B. Therefore 1 upon Ne is equals to E suffix H upon JB. Okay, in this equation this is known as 1 upon Ne is known as Hall coefficient. This is known as Hall coefficient. Hall coefficient is denoted as the R suffix H. R suffix H is equals to 1 upon Ne is equals to Eh upon JB. Okay, hence the Hall coefficient is defined as the Hall coefficient. This is the 1 upon Ne or H 1 upon Ne. The Hall coefficient is defined as the ratio of Hall electric field to product of current density and magnetic field. Current density and magnetic field. This is the Hall coefficient. Finally, the Hall coefficient is defined as the ratio of Hall electric field to the product of current density J into magnetic field B. Thus, the value of Hall coefficient is the negative when the charge carriers are electrons. This is the RH. RH, R suffix H. The Hall coefficient is the negative. The charge carriers are electrons. RH, Hall coefficient is the positive. The charge carriers are holes. This is the totally Hall effect and Hall coefficient. The applications of Hall effect is very useful to phenomenon of helpful to determine the type of semiconductor because if Hall coefficient is negative, then the charge carriers are electrons. Hall coefficient positive, the charge carriers are holes. From these two conditions, the semiconductor is the P type of semiconductor and N type of semiconductor. By knowing the direction of the Hall voltage, one can determine the P type of semiconductor and N type of semiconductor. So from this Hall effect, helpful to determine the types of semiconductor. Okay, next, calculate the carrier concentration, the experimental concentration R suffix H, Hall coefficient. This is the 1 upon Ne. The N is equals to 1 upon R suffix H E. This is the here N is the carrier concentration. Charge carrier concentration. Charge carrier concentration means number of charge carriers. Next application is the determine the mobility. The mobility expression for the electrons mu n, holes is the mu p. Expression in the terms of Hall coefficient is given by the mu. Generally mu is equals to sigma or suffix h, where sigma is the conductivity. So this is the mobility of charge carriers. Next, from the Hall effect, we determine the magnetic flux density. B is equals to VHD upon RH upon I. Okay, these are all applications of Hall effect.